Hello and welcome to Calculus. In this lecture, we're going to be looking at a very important application of the tangent line called the tangent line approximation. Please make sure you print and follow this lecture with my notes on tangent line and local linearity number 2. Let's begin. So, what is the tangent line approximation? It's a technique to evaluate the output of a function near an input where the function is differentiable. What did I just say? So it's a technique to evaluate the output of a function, near a point where the function is differentiable, That means what? That means has a derivative. How do we do this? Well, let's look at it graphically. So let's graph a function that is differentiable at a point that I will call A, right here, A. So let me graph the function like this, and let's plot f of A. So here is this length, the length of this segment is f of A, right? It's about here, and this is f of A. Okay, so let's draw the tangent line. If it is differentiable, then it has a tangent line. Let's draw the tangent line. Here we go. All right. How can I evaluate the function, approximate the function near A? So now let's take a point near A. I'll take it right here. For the sake of the picture, I'm going a bit far, but imagine it's zooming very closely, okay? So let's call this point X right here. I want to evaluate f of X, or rather I want to approximate the value of f of X. So the exact value of f of X is the length of this segment right here, right? The length of this segment. So this is the exact value of f of X right here. But instead of following my graph, my function, right, and get the exact value, what I'm going to do, I'm going to follow my tangent line. I'm going to look at this output right here. Here's f of X plus this thing right there, okay? I'm going to follow the tangent line to evaluate f of X. How can I do this? Well, this is a tangent line at the point A, f of A, okay? So what we do, we go at f of A. So I'm looking at this piece right there, f of A, which is also here, right? This is f of A right there. I'm looking at the length f of A, and to that, I'm adding my rise, right? And what's a rise from f of A? What's a rise? The rise is the slope times the run. Okay, well, the slope, this is the slope of the tangent line. So I'm adding right here, the slope is f prime at A, the slope of the tangent line, and the run, well, what's the run right here between x and A? It's x minus A. So times x minus A. And I'm adding that to f of A right here. So I'm going to say, and I'm going to assume basically you're making a mistake, right? Here's my mistake right here. This is a mistake I'm making by approximating f of X by the tangent line right here. This is what I'm going to say is about my value of the function. This is about. This is exact, and this is about. Okay? So what formula do we land on? Well, we have that f at X is about f at A plus the rise from A plus, so f prime at A times x minus A. Okay, so we will see this formula for the tangent line approximation, and you see it's an approximation of f of X at A, where I have my tangent line. So of course you understand, if I go very far from A, then that distance right here, that space, that error that I'm making is getting larger and larger, right? The distance between the graph and the tangent line is increasing, right, the further I go. Well, it also depends on the function and how the function curves, right, the concavity. Sometimes we also look at another formula that is really the same with different letters. Instead of x, I will call that a plus h, right? So now the run is going to be h, okay? And the formula becomes f of a plus h is about f at a plus the slope is still f prime at a times my run, so it's h, okay? It's really exactly the same formula, but instead of x, I'm looking at x as being a plus h, right? I replace x by a plus h. And if you do that, then x minus a, right? X minus a right here, x minus a, if you move the a right there, becomes h. Here we go. Okay? So let's apply this formula to a couple of problems. So in the first example, taken from my notes, I'm going to approximate the output of the function ln at 0.6, 0.7, and 1 using the output of ln at 0.5, the output of ln and the output of its derivative at 0.5. Okay? And I'm going to do that with the calculator, of course. So first, let's write the formula. So ln at 0.6 is about ln at 0.5 plus, so the rise, right, from ln at 0.5. So that's the slope, ln prime at 0.5 times the run. Well, what's the run between 0.6 and 0.5? That's 0.1. Okay? So what is ln at 0.5 and ln prime at 0.5? Let's use the calculator to compute that. So in y1, let me put the function ln x right here. Here we go, ln x. In y2, I have my derivative, right? So now to get ln at 0.5, I can just go making sure my table is on ask right here and check out some table of values. All right, so at 0.5, what do we have? So the function is negative 0.6931 and the derivative is 2. Okay, so we could enter that, but this is an approximation, right, ln at 0.5, so am I going to enter negative 0.70? Well, let's try to get the exact value. Look, for that, in y3, I'm going to enter the tangent line approximation at 0.5. How do I do it? Well, that's very simple. So it's a function at 0.5, so that's y1 at 0.5, y1 at 0.5 right here, plus the rise of the function from 0.5, the rise following the tangent line. So the slope is y2 at 0.5, right, the derivative at 0.5. So y2 at 0.5 right here times the run, and the run is x, whatever my x is going to be, x minus 0.5, right? So x minus 0.5, okay? And my first value for x is 0.6. So now let's check out the table again, and let's enter in the second one right here, let's enter 0.6. Okay, what do we have? So the value of y3 at 0.6 is about negative 0.5, okay? So it's about negative 0.5. So this right here. So this is about negative 0.7, right? Plus, and we said 2 times 0.01, and this is about negative 0.5. Okay, what is the exact value of the function at 0.6? So let me take the calculator again. This right here, y1 at 0.6, this is the exact value of the function. So this is negative 0.51. All right, so this is negative 0.51. And now let's compute the percent relative error. So it's exact minus approximative divided by exact times 100. So again here, I'm going to be lazy and I'm going to ask my calculator to do it for me. I'm going to put that in y4, right? So let's enter the approximative error. So what is the exact? That's y1, right? So absolute value. Where's the absolute value? You go to math, you go to numerical, absolute value. Here we go. Absolute value of, so approximate minus exact, or exact minus approximate. So parenthesis, it's a subtraction. Exact, that's y1. So y1, here we go, y1. Minus approximate, that's y3, right? That's my tangential approximation. I put it in y3. y3, so vars, y-vars, function y3, right here, divided by exact. So divided by y1, vars, right here, y-vars, function y1. Okay, and let's read it directly in percent, so times 100. Here we go. So now let's check out the mistake we're making, the error, the percent error we're making. So the percent error I'm making at 0.6 is about 3.46%, right? 3.46% right here. So 3.46%. And now with all these functions, it's going to be pretty simple to approximate the value at 0.7 and find the exact value. We're just going to look at the table, right? So let me go there. Let me go down right here. And let's enter 0.7. So 0.7. Okay. All right. So this is my exact value, negative 0.36. I guess. So the exact value is negative 0.36, while the approximate value is, so what is that? This is about negative 0.293, so negative 0.29, right? Negative 0.29. So this is negative 0.29, and the percent relative error is 17.8%. So 17.8%, 17.8%. Okay, let's look at the value at 1 right here. So again, I'll let you fill out the table here. It's easy, you just copy what's on the calculator. It's kind of cumbersome for me to move screens like that. So at 1, what is, okay, so the output of the function, well, ln1 we know it's 0, right? So ln1 is 0. The tangent line approximation would give you a 0.3, and the error, well, it's not defined because ln1 is 0, so you're dividing by 0. So actually, let's take one that is right past 0.1, right? Past 1, so 1.1. So let's see what we have here. Okay, look, the exact value is 0.09. The tangent line approximation will give you a 0.50, and the error is now 400%. You see, the further away you go from 0.5, and the larger the error. Why is that? Well, because again, if you follow the tangent line at the place where the graph curves a lot, like 0.5 for example, if this is like 0.5, and you go far away, you know, 1.1, then the mistake you're making between the exact and the approximate is getting larger and larger. If you stay close to 0.5, right, the mistake is not too big, but the further away, the larger it gets, okay? All right, what's going on at 2? So now we have to be careful, right? It's a tangent line approximation at 2. So in my calculator, I need to change what's in the tangent line approximation. It's no longer at 0.5 right here, but it's at 2. So let me go right here, let me put 2, let me delete the 5 right here, and in the slope, it's a slope at 2. So let me enter 2, let me delete the point right here, and this is the distance between x and 2. So 2 right here, and delete. Here we go. In y3, I have my tangent line approximation at 2. I'm not going to fill out the table, I just want to check out the values. 2.1, 2.5, and 3. So let's look at the values. 2.1, 2.5, and 3. Here we go. So 2.1, 2.1, here we go. 2.5, here we go, and 3. All right. So exact, approximate, exact, approximate, exact, approximate. Look at my error, 0.16%, 2.9%, 8.1%. How come this time, if I move 1 unit, right, at 3, that's 1 unit from 2, I'm just making a mistake of 8.6 unit, while previously my mistake when I moved 1 unit was like 400%, right? How come it's so small? Well, that again is due to the shape of the graph at 2. What's going on here is that at 2, we are here, if I continue right there, right? If I'm at 2, the graph is not going to curve as much, right? And so the tangent line is going to stay, this is like 2, for example, right? And this is 3. The tangent line, because the graph doesn't curve as much, stay closer. You see all these errors right here? They're not growing as fast as they were growing around 0.5 because the graph curves much more here than here. The graph is flatter here. It doesn't curve as much, right? So the curvature of the graph is an important consideration when we do the tangent line approximation, okay? Let's move on to the second example. So this is another example taken from my notes, so please follow from my notes, okay? I do advise you also to read the notes, of course. Let's move over this example. I'm giving you the function, and this time, for the first time, I'm giving you the expression of the derivative function. This is something we're going to be covering in the next unit. But I'm telling you, if the function is root x, then the derivative function is 1 over 2 root x. And I'm asking you to evaluate square root of 18. So I'm giving you an indication of where right here, but usually you don't have this indication, right? So you want to evaluate square root of 18. This is the output of f of x at 18. And I need to use a tangent line approximation. So near 18, what square root output do I know very well? Well, I know the square root at 16, right? So this is a kind of reasoning you will have to have on your own, okay? So near 18, I know the square root at 16, and that's what I'm going to do. I'm going to do the tangent line approximation at 16. So the square root of 18 is the output of the function at 16 plus the output of the derivative at 16. So here we go. This is the derivative right here. So 1 over 2 square root of 16 times the run between 18 and 16, so 18 minus 16 right here. And you see for these, I don't even need a calculator. So what is the square root of 16? Well, so it's 4 plus 1 over 2 times 4, 8 times 18 minus 4, 2. So it is 4 plus, that's 1/4. So it's about the square root, so let me rewrite it here, actually. So I'm saying, with the tangent line approximation, I'm saying the square root of 18 is about 4.25. I did not use any calculator. I just did one addition, one multiplication. This is what you do with the tangent line approximation. It's just an addition and a multiplication, instead of extracting a root, which can be much more difficult, okay? And there would be many more operations than one addition and one multiplication, all right? So can we check this right here? So let me see. Let me go right there, home screen. What is square root of 18? So square root of 18 right here. And this is, oh, look at that, 4.242. It's not too far. And again, 18 was 2 units away from 16, okay? So I'm not, it depends what you call close, but this is not very, very close. And I got a pretty good idea what the square root of 18 is, right? So this is not bad at all. Next one, I want to evaluate square root of 52. So again, I'm telling you where, but if you think about it, you know, what output of the square root do you know near 52? Well, 49, right? Square root of 49 is 7. So I'm going to say that the square root of 52 is about square root of 49 plus, so now the slope, so again the expression of the derivative is given right here, 1 over 2 root x, right? So 1 over 2 square root of 49 right here times times, so the difference between 52 and 49. 52 minus 49. Okay, so what do we have? We have 7 plus 1 over 14 times 3. So it is 7 plus 3/14. All right, so let's see what 7 plus 3/14 is with the calculator. I don't really need a calculator right here, right? But it's going to be faster. So 7 plus 3 divided by 14. This is 2.71. Well, let's check out the square root of 52. So square root of 52 is, oh, look at that, 2.71. Wow, this is pretty good, right? So again, why this time, if I went 3 units away from 49, I got a better approximation than if I move 2 units away at 16, again, because of the curve. Square root goes like this, right? Goes like this. So the closer you are to 0, right, 16 maybe, I don't know, maybe right here, the closer you are to 0, the more it curves. The further you are, the less it curves, and so you can go further away from the tangent line and you still have a pretty good approximation than if you move at the same distance right here. Okay, it would be larger here than here. All right, that's why. And therefore, for the last example, let's see, 125, I'm 4 units away from 121, right? Let's see how good approximation we get. So square root of 125 is about square root at 121, which is 11, plus, so expression is 1 over 2 square root at 121, times, so 125 minus 121 is 4. So this is 11 plus, so 1 over 2 times 11, 22 times 4. So it is 11 plus 2 over 11. All right, so let's see what that is. So 11 plus 2 divided by 11. And this is 11.1818. Okay, now square root of 125 is, now you see, this is really good. This is really good, right? Okay, all right. So let's move on to another example now. So this is the last one. This is one from the book. So page 108, number 27. Annual net sales in billions of dollars for the Hershey Company, the largest US producer of chocolate, is a function S of t of time t in years since 2000. Interpret the statement f of 8 equals 5.1 and f prime of 8 equals 0.22 in terms of Hershey's sales. So f of 8, so f of t is the annual net sales in billions of dollars, right? After, and t is years after 2000. So f of 8 equals what? F of 8 equals 5.1 means that in 2008, Hershey's net sales were $5.1 billion. Billion dollars. I don't think there's an S at billion, right? I never know this one. $1 billion, right? It's in billions of dollars. Yes. So that's their revenue in 2008. What does it mean that f prime at 8 is 0.22? So now, how do you interpret f prime at 8 is 0.22? Well, that's a derivative, right? Derivative is the instantaneous rate of change. So rate of change is output over input. Output is in billion of dollars, right? Billion of dollars. Input is in year. So that means that in 2008, Hershey's net sales increase, right? It's positive right here. It's positive. Increase at $0.22 billion per year, right? Per year. That's what it means. It's the meaning of the derivative. And so now, estimate f at 12. How do we do that? We're going to use the tangent line approximation, right? So f at 12 is about f at 8 plus the slopes times the run. The slope f prime at 8 times the run. 12 minus 8, 4. So f at 8 was 5.1, right? 5.1 plus 0.22 times 4. 0.22 times 4 is 0.88, so it is 5.1 plus 0.88, which is 5.98. Okay, so I believe that in 2012, right, in 2012, this is Hershey's, so billions right here. This is Hershey's revenue. Again, it's an approximation. We're really assuming that the revenue, the function for the revenue doesn't do this, right? Or it would be really off. We're assuming it's going to vary smoothly and it's going to curve upwards, but hopefully not too much. Okay, so there's a lot of assumption there. All right, thank you for watching.